These are the laws for circuits. In Physics 12, we actually call these Kirchhoff's laws. He was a Russian physicist. I think he was Russian. And he came up with two massive rules that will help you solve a circuit. He came up with a voltage rule, and he came up with a current rule. Now, by a circuit, what I mean, Evan, by a circuit is any set of wires that ends up making a closed loop so that the electricity can flow. In other words, just a wire sticking by itself and not attached to anything, these rules don't work. But if you eventually can make a full, well, a circuit has the same word as circle. If you can end up back where you started from, that's going to be a circuit. You ready? The first one is what we call the current law. First of all, we're going to say this. Current in a circuit flows downhill. It flows from the positive terminal through the rest of the circuit to the negative terminal of the voltage source. Now, that's not the way that electrons flow. Remember, we said that electrons are the ones that are actually moving. Electrons flow from negative to positive. But we said it's so much nicer, Martin, just to pretend that the positives move. I've done my rant about how Ben Franklin named them wrong. Should have had one positive and the other one that protons should be negative. Really, if we had our way, we'd do it that way. So current is which way the positives would want to move if they could. Okay? From positive to negative. And what I really mean is your first job in any circuit is find the voltage source, which for you folks this year is going to be a battery. There's other voltage sources. There's plugs. There's capacitor. There's others, but starting off basic. So rule 1, downhill. Cole, you ready to go? Okay. Rule 2, at any junction, any place where wires meet, current flowing in has to equal current flowing out. I've told you, Josh, that a circuit is like a ski hill, and I've said that current is like the number of skiers. In my ski hill analogy, CL, the current law, that's my abbreviation for current law, you may have noticed I tend to abbreviate, simply means that if 3 skiers converge on an intersection from 2 different paths, you know what? If you have 2 amps coming in here, and if you have 1 amp coming in here, how many amps do you have flowing out? If you have 2 amps flowing in and 1 amp flowing in, do the math in your head. How many amps must flow out, Matt? Yes. You don't realize just how profound that is. That may seem simple, but it turns out that alone can bail you out of a lot of stuff. All right? Already we can start to figure out unknown currents. So when I solve a circuit, here is my diagrams of circuits. Who remembers, what does this symbol stand for? Cell or a battery, we'll call it a battery. Voltage source. What did these jagged lines stand for? These are resistors, and now I'm being generic. Ibrahim, the resistor, it can be a light bulb, it can be an iPod, it can be a microwave. I don't care. I'm doing very, very generic general circuits here. First thing that I always do is I find the battery. There it is. Which is the positive part, the long line or the short line? First thing you always want to do, find the long line, draw an arrow, that's downhill. Now you know how you're going to go skiing through the circuit. We go skiing, we go skiing, we go skiing. How many amps right here? 1.75. How many amps right here? Still 1.75, because no skiers could go anywhere else. Let's fill that in. Keep skiing, keep skiing, keep skiing. How many amps on the bottom here? Yeah, loud and proud. Okay? In other words, skiers' current doesn't vanish. Whatever current you start with, that's how much you end with. That's Kirchhoff's law. Whatever current flows in equals current flowing out. Let's do a more interesting one with some junctions. In fact, I think I can make these a little bigger. Can I go 250? Yeah, I can. So, there's the battery right there. That's downhill. Nick K, how many amps right here? And that is, if I walk back, the total current, because that's how many amps left the battery. Or if my ski hill analogy, there's 3 skiers on this hill, grand total. How many skiers? How many amps? Okay. How many amps went this way, Nick? How many amps must have gone this way? Can you do the math in your head? Has to be 2.2. Let's follow this junction. How many amps right here? Still 2.2. How many amps are in this resistor? Still, this resistor would receive 2.2 amps. We'll talk about what's going on in there in a bit. How many amps? Oh, which direction is the current flowing right here? Is it flowing to the left or to the right? Let's do that. Oh, and how many amps are right there? 2.2. How about right here? How many amps are right here? I have 2.2 coming this way. I have 0.8 coming that way. 3 or 3.0 if you want to even add a decimal. So how many amps right here, Alex? And which way is the current flowing right there? Current flows downhill, and current doesn't vanish. Current in equals current out. Okay? If you really want to be fussy, Maddie, what we're actually saying is charge doesn't vanish. Kirchhoff's law comes out of something that we call the conservation of charge. Okay. Let's just up the ante and get more complicated. Example 2 says, show the direction of each current and find the unknown currents. Okay. I almost always start, I find the battery, see it? And I label which way is downhill, because Ibrahim, that's going to help me do all the math. So I'm going to go, that's downhill. That's downhill. I guess right here at this junction, that way and that way are downhill. Right? Let's go along the top. Right, you know what? I guess right here, this way and this way are downhill. If I follow this, which way is downhill right where my eraser is, left or right? Which way is the current flowing right where my eraser is? Left. How about right down, you know what? I think the current is going that way, yes? And that way. Did they tell me how many amps are leaving the battery? Not exactly. So let's walk, let's go skiing downhill. Here's a junction. How many amps went this way? How many amps went this way? How many amps must be incoming? See it? How many amps right here? How many amps right here? More important, how many amps came out of the battery? This is the current law. I bet you the question just fell apart. Now all we're going to do is ski the different ski runs, counting up the number of skiers. Or we're going to go through the different circuit paths, analyzing how many amps. Brady, how many amps went this way? How many amps went this way? How many amps must have gone this way? Has to be. How many amps right here? How many amps in this resistor? How many amps right here? Has to be. How many amps right here? Ah, because the 2 and the 3 joined up. Really, if you want the ski analogy, we came to a fork and we shook hands. 2 of us went this way, 3 of us went this way. Now, the only problem is we can also have decimals like 2.8 amps, and you can't have 0.8 of a skier. But 2 skiers, 2 amps went this way, 3 amps went this way, and they agreed they would meet up down here. How many amps right here? Yep. How many amps right here? Gotta be. Is that okay? All I can do is make it, Drew, trickier with more complicated diagrams. Oh, like this one. Where's the battery? Where's the source of voltage? The bottom? See it? Which way is downhill, to the left or to the right? To the right, let's put an arrow. Downhill. This is downhill, yes? And I guess that's downhill, that's downhill. There's 3 forks in the trail, and we all go our separate ways. That's downhill, that's downhill, that's downhill, that's downhill, that's downhill. This is downhill. Downhill, downhill. I guess that way is downhill, and that way is downhill. Is that okay, Drew? Okay. Drew, did they tell me how many amps are leaving the battery, how many amps are leaving the voltage source? How many amps went this way? How many amps went this way? How many amps went this? You know what? I don't think I can figure it out yet. Can I? Let's keep going. Oh! How many amps right here? Is that all the skiers? Ah. So this was sort of a trick question. Did they tell me how many amps left the battery? If I look carefully elsewhere, the answer is, yeah. How many amps? Okay. How many amps right here then? How'd you figure that out? How many went this way? 0.5. How many went this way? 2. So what's left over? It's got to be 2.5 amps. Finish it off, Drew. How many amps must be over here? Got to be 3. Y'all with me? Okay. That's the current law. Did I have one more? I can't remember. Oh, I do. I do. One more or 2 more? Yeah, 1 more. Okay. Brooke, see the battery? Which way is downhill? Up the page or down the page? Up. Sorry, up is down, I realize, but you know, it's what we got. Do I know how many amps left the battery? 4 point. Okay, good. Let's label, that's downhill, that's downhill. Probably some of you will get good enough that you don't label as much as I am, but in our notes so that we know what the heck we're doing, let's do this. So how many amps right here, Brooke? How many amps went this way? How many amps right there then? Yep. That A didn't show up very good. Let's try that again. How many amps went this way? Yep. How many amps over right here? Oh, how many amps? How many amps right here? Yep. By the way, this will be most of the written section of your test. I'll give you a bunch of blank circuits with a few clues, and it's just going to be, you'll see I'll have letters, and it's going to be fill in the rest of the blanks. I usually do 1 mark for each of the blanks. Very last one, Brooke, how many amps right here? Yeah. That's the current law. Current in equals current out. Oh, and if you want a direction, current flows downhill. By the way, are you seeing why it's nicer to think that downhill is positive from the positive? It's just much nicer to think that way. Okay. Next page. Kirchhoff also gave a voltage law. I'm going to give it to you the way he explained it, and then we'll show you my ski hill analogy, which will make it easier. But here's what he said. If we walk around a circuit, if we end up back where we started from, any voltage gains equal voltage losses. I need an extra S in there. Or the voltage gains equal the voltage drops. Huh? Maddie, in terms of my ski hill analogy, voltage gains are the battery. Voltage gains are the battery. And it basically says this: any voltage you gain from the battery, you have to lose going through resistors before you get to the bottom of the battery. Voltage gains are like the chairlift, the battery. If you want to get to the bottom of the mountain, if you want to get to the bottom of the chairlift, you have to lose all the voltage that you gain from the chairlift. Okay, so I wrote here, in terms of the ski hill analogy, the voltage law simply says that the chairlift takes you to the top of the mountain. From there, as you ski down to the bottom along any path, the sums of the drops must equal the height of the mountain. It's easier if we do some. So now it says, find the unknown voltages and voltage drops. So here's a circuit. That way is downhill. That's how I'm going to ski this. How big is the battery? How many volts are we gaining in this circuit? 20. Or How big is the chairlift? 20 volts. How high is the mountain? 20 volts. So how many volts do we have to lose before we get to the bottom of the battery? Same answer, 20. Okay? So right here, I'm 20 volts high. Keep skiing, keep skiing, keep skiing. Have we gone through any resistors yet? I'm going to ask you the same question. I'm just going to phrase it differently. Have we gone down any ski hills yet? Because resistors are my ski hills. No. So how high was I right here, Brady? 20 volts. I know it sounds strange. 20 volts. How many volts do I have right here? 20 volts. Turns out this resistor uses up 8 volts. How many volts are we here now? 12. They didn't tell me how many volts this resistor uses. I don't know how high, but wait a minute. Did I end up at the bottom of the chairlift? So how high am I right here? If I end up at the bottom, what would be a good voltage that would reflect the bottom of the mountain? How many volts as a number? Cole? 0. So if I had 12 volts, how many volts must I have lost through this resistor? Has to. And that's what gets me to 0 volts just below it. This is the voltage law. Let's try another one. Okay. I think I got to make this one a little bit smaller. There we go. Here is where, at first, it's going to seem strange, but if you wrap your brain around it in terms of a ski hill, it makes sense. Chairlift, how high is our battery? How high is our mountain? How many volts is our source? Those are all the same question. What do we got? So how high are we right here? Still 10 volts. Right here, there's a fork. This way is downhill, downhill, and down. That's a terrible arrow. Let's put the arrow right there, downhill. Yes? We have to pick a path. You know what? Let's ski down this path here. Okay? How high are we? How high are we right here? Have we gone down any hills yet? Say no. So what's the voltmeter going to read right here still? 10. Then there's an unknown voltage drop. Oh, how high am I here? So how many volts high must this hill be? Yes. How high is the voltage measured right there? 0. Now, Carter, you might have decided to go this way instead. So right here, before we split up, how many volts are we at? 10. Keep going, keep going, keep going. Have we gone down any hills yet? How many volts are we at? I go through an unknown resistor, an unknown hill. I don't know how high that hill is. I don't know how high I am there. But you know what? I don't go down any more hills, and I'm at the bottom of the mountain. So how high must I be right here? How many volts must I have lost here? Yeah. And this bugs kids because they say, Mr. Dewick, that resistor took 10, that resistor took 10. Isn't that 20 volts voltage? What we're really saying is each resistor used up 10 volts. Let's do another one. This way, this way, this way, this way, this way, this. Okay, I know how I'm skiing. Can you see, wow. Danielle, can you see there's two paths? Some skiers can go this way, and some skiers can go that way. Some current can go this way. Some current can go that way. We'll ski each run. Ready, Danielle? How high are we when we leave the mountain? So how many volts right there? I guess every skier goes through this hill. How many volts high is this hill here? And it's a loss because we're using up energy going through the resistor. So that's why I wrote the word drop here. So how many volts do you think we would be at, Danielle, right here? 4. How many volts right here? How many volts right here? Because we haven't gone down any new hills. I agree. Whee! We go down a hill. Did that get us to the bottom of the chairlift? How many volts must I lose going through this resistor? Leaving me 0 there. You okay with that, Mason? Let's go back. Mason, do you remember how many volts did we start out with? How many did we lose going through here? Leaving. So how many volts right here? Same answer. How many volts right here? How many volts right here? Yep, because we haven't gone down any new hills. Mason, we go down this hill. Whee! How many volts high are we here now? Yeah. So how many volts did we lose going through this resistor? Yeah. Now, Josh, this diagram is getting really, really cluttered. What we're going to start to do is only label the battery voltage and the resistance losses. We're not going to label all the wires in between because that just really mucks up the diagram. And also because nothing's happening in the wires. Is that okay? Let's try one more. Who wants to go skiing? Because that's really what we're doing. Tensei, okay. Raise your hand. Tensei, you ready? You ready? You ready? How many volts right here, Tensei? Oh, hang on. Let's label which way is downhill. First of all, there's the battery, yes? Which way is downhill? Upwards or downwards? Good. So I'm going to go downhill, downhill, that's downhill, that's downhill. I'm going to ski that way, I'm going to ski that way. Yes? All right. How many volts high is this mountain? It's a big mountain, big battery. How many volts right here? Yes. Everybody, all the current, all the skiers go through this resistor. How many volts do they lose going through here, Tensei? Leaving. They have 60, they lose 15, leaving. So how many volts right here? How many volts right here? Really, how many volts right here? Good. Let's fill that in. Okay. How many volts do we lose going through this hill? So how high did we start? No, look up. How high did we start? 45. We lose 18. This is what you were calculating. What does that leave right there? Whatever 45 take away 18 is. 27? Yay! Keep skiing, keep skiing, keep skiing. Always going downhill, never going uphill. So if you're wondering, Mr. Duick, how do I know not to turn this way? Because you don't ski uphill, right? Downhill. How many volts right there, Tensei? How many volts right here? Yep. And then I go down one more hill. How high am I here? How many volts must I have lost going through this hill? Yes. Hey, we skied. You know what? You're doing so well, Tensei. Let's finish this. Let's finish this. Let's go back because we haven't done this. How high are we right here? 45. So how high right there? 45. How high is this hill? 10. So how high are we right here now? Careful. 35, isn't it? Yeah. 30. By the way, be careful. It's easy to make a math mistake, and that'll domino through the rest of the question. So just be really careful doing the arithmetic. I don't know how high this hill is. Oh, how do you know? Because how high am I right there? Got to be still 27, right? Because otherwise, how could they have met up at the same voltage height? So you're saying that's 27 volts, so this must be 8 volts. Yes, well done. You okay with that, Christian? This is the voltage law. Except this is way too much writing. So I wrote here, although it's helpful at first to label voltages at each point in the circuit, too much writing. It's desirable at this point to label only the gains and the drops, the batteries and the resistors for you guys this year, because that's all it's going to be. So in all of the following examples, the voltages next to resistors are understood to be drops, negative, subtract. The voltages next to batteries are understood to be gains, increases, chairlifts. Let's put it all together, except now we're going to add one more thing. We're going to add V equals I times R. We're also going to add I equals V over R. And we're going to add R equals V over I. And we're going to add P equals V times I. Putting everything together. Okay? This is where I say, I like this question, I like this. These are the kind of circuits you're going to get on your test in a few days. Test is probably going to be either at the end of next week or the beginning of the week after. You ready, Hannah? See the battery? Find that first. Label which way is downhill. When I solve a circuit, Brian, I always try and find the total current leaving the battery. You're going to learn, if you know the total current, the question falls apart. Did they tell me the total current leaving the battery? Well, not direct, or did they? Brian, how many amps right here? How many amps right here? How many amps right here? How many amps in the coming through the battery? Okay. And that's the total current because there's no, that's the source of this gear. I'm telling you, the question's going to fall apart. Okay? The other thing I'm going to tell you is anytime I know two things, I know four things. So, you ready? How many volts? How many volts do I lose going through here? 6. Leaving how many volts? How many volts must I lose going through there? Yes. Ready? How many amps? How many amps? How many amps right here still? How many amps went this way? So how many amps went this way? How many amps? Let's fill that in. How many volts? What do we lose here? Leaving. How many volts must I lose in that resistor? Now this bugs kids because a lot of students will say, well, Mr. Dewick, it's 18 volts from the battery, but if I go 6 plus 12 plus 12, that's 30 volts. Okay, voltage in the circuit does not add up to the battery. But the voltage in any closed path and any circle will add up to the battery. 18 up, 18 down. Or, so you could ski this path here, or you could ski that path there. Those are both closed circuits, and I'm telling you, in those, 18 up, 18 down. We're not done. What's the resistance there? How could you calculate how many ohms that resistor must be if it uses up 6 volts and it absorbs 8 amps? How many ohms must it be? How can you calculate that? Yeah, more specific. I want the answer. Isn't it 6 divided by 4? 1.5, right? Right? Ohms. Hey, how many watts of power does this resistor use? If this was a light bulb, how many watts is this light bulb? How'd you get the 24? What I'm telling you is, in any section of a circuit, Jaden, if I know two things, I can find all four things: power, resistance, current, and voltage. 24 watts? Okay. What's the resistance of that bulb right there? Or that appliance, or whatever it is? How many ohms is that middle one? Four? How can you count? Oh, it's V divided by I, yes? Voltage divided by current. So now 10 say all of these equations here totally fair game as far as, why do I have a big black dot there? I don't know. Is there a black dot there in your copy? Yeah? Oh, no? Okay. I don't know why that's there, but it's there. Okay. Sorry, how many ohms did you guys say this one was? This one, still 4 ohms, the middle one. If that's a light bulb, how many watts is it? 36. Okay. What about the right hand, Evan? The right hand resistor, how many ohms does it have, Evan? 12 ohms. How many watts is it? I times V times I, right? V times I, 12 times 1. Is that okay? So let me give you a cool Physics 12 question. In Physics 12, I wouldn't give them this circuit and say, solve everything. Instead, I would say, in this circuit, there are 3 light bulbs. Which one's brighter? Which is the brightest bulb? The left one, the middle one, or the right one? How do you know? It's the wattage, right? What you've learned in light bulbs, wattage is brightness. Okay? So now we've taken it, Nick, one step further. We can start to predict what kind of a circuit this would look like. Light bulbs is my usual fallback resistor analogy, but we can talk about other appliances another time. But the nice thing about light bulbs, more power equals brighter. My mom says I'm the brightest bulb. No, she means something different. Okay. Let's try another one. Going okay with this, Katie? Let's go skiing. You want to go skiing? It's a nice sunny day. Let's go skiing. So it said, basically you can see, I'm going to fill in any missing blanks. On a test, this will be your question. What I'm also doing with you guys today is also showing, you know what, you can also find resistance and power and anything else we need, because why not? Downhill. Downhill, 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 downhill. If I know the total current leaving the battery, the question falls apart. Do I know the total current leaving the battery? Can I figure it out? How many amps must have been leaving the chairlift? How many skiers must have been on this hill? How many amps are leaving the battery? Same way, same question, just different ways to phrase it. Did you figure it out? How many amps went this way? How many amps went this way? How many amps went this way? How many amps were right here then? How many amps are right here then? How many amps are right here then? You know what? 2.5 amps. Often I'll just label it right by the battery. That's like my woohoo! This question's going to fall apart. I got to be careful, but I'm telling you, this question's going to fall apart. So how many amps in this? While we're here, what's the resistance of this? You need your calculator. Well, maybe not. It's going to be 20. Are you guys okay with how we're calculating? It's going to be 21 divided by 2. It's okay. So this is why I said if you don't show work, I'll assume you went straight to your calculator and did the math. What is it? 8.4? And for giggles, how many watts of power does this use? I think that I can do in my head. 21 times 2.5, it's going to be 42 plus 10.5, 52.5? Yeah, okay. I will be fussy, put units, okay? If you just put a number, I'll take a half mark off. Let's keep going, Katie. How many amps came through here? How many oh, you know what? They gave me the amps. So, voltage. How many volts did we start out with? How many volts did we lose through here? How many volts did we lose through here? 21, leaving 14. Sorry, but I'm walking people through the mental steps, yes? So how many volts right here? How many volts do we lose going through this hill? Must be. How many volts do we lose going through this hill? Okay. Now, ready for some terminology? We say these two resistors are in parallel because they're splitting up the current. They're in parallel. And you'll notice if you have resistors in parallel, you actually lose the same voltage going through each of them. While we're at it, what's the resistance of this bulb? I can do this one in my head. It's going to be V over I, 14 divided by 1. In your head, Matt, 14 divided by 1 is? Woohoo! It's the 1 times table. I'm good at that one. And Matt, how many watts is this? I can do that one in my head because it's going to be V times I. So see the numbers? Can you go V times I in your head? How big is V? How big is I? So you're telling me the answer? This kind of, sorry, when you have the 1 times table, it turns out, yeah, you got 14 volts, 14 ohms, 14 watts. Okay, but it is what it is. Katie, let's finish this off. What's the resistance of this? And I don't think this one will work out evenly. It's going to be a repeating decimal, I'll bet you. What is it, Katie? 14 divided by 1.5, right? This is also for you that have the cheap calculators to make sure that your calculator can handle this. I think they all should. 9.333. So I'll go 9.33. And how many watts? That I can do in my head. 14 times 1.5. 21, yes? If these are light bulbs, which was the brightest light bulb? The left one, the middle one, or the right one? Okay? The top left one, right? This guy. Or if these were appliances, which one uses the most power? This one is the most expensive to run. Which one uses the most current? Right? 2.5 amps, 1 amp, 1.5 amps. Which one uses the most current? This one here as well. Which one would probably get the warmest? Probably that one. This is all stuff if you're designing a house, if you're designing a circuit, if you're building something, now we can start to make predictions. Again, Sierra, I'm keeping it basic. We're looking at simple resistors and batteries, but all circuitry builds from Kirchhoff's laws. Next page? No, never mind. One down. Anybody want to try this? Let's go skiing. Who wants to try this? Sure, Alex. Ready? You kind of twitched at me? Okay. First thing I always do is I label which way is downhill. I don't want to accidentally go the wrong way. Right? Okay. Did they tell me how many amps came from here? No? No. Oh, okay. So, rules. Josh, you going to make it? That was a long blink. I always look for total current first. Did they tell me total current? Say no. Then I look for any resistor that has 2 things on it. Nothing, 1 number, 2 number. This is where I'm going to start. This is where I'm going to start. Okay? How many volts? How many amps? Okay, I can fill that in. How many ohms? Please don't use a calculator. I think 35 divided by 1. Okay? This is how this question is going to fall apart, though. How many volts do I lose going through this ski hill, going through this resistor? No. How many volts do I lose right here? 35? Yes? You already went to the next step. Let me walk everyone else through it. How many volts does this chairlift, does this battery give me to start out with? 40. And if I go this way, is that a closed path that'll get me to the bottom of the ski hill? So that means my voltage gains, the 40, has to equal my voltage losses. And you're telling me I lost 35 there. How many must I lose here? Okay. So far, so good. Oh. See that hill? That ski run? See it? How many volts do I gain? How many volts do I lose on this hill? Whee! How many volts must I lose on this hill for the math to work? Loud and proud. Hey, I now know two things over there. How many amps must this be? I know the resistance. I know the voltage. How many amps? Be nice if I had an equation with an I by itself. There's no power. There's another equation with an I by itself. Do I know V? I know R. Yeah. Can you do it in your head? Not times. Over means divide. 7. Yes? Yeah. Hey, by the way, how many amps went this way? How many amps went this way? How many amps must be right here? 8. How many amps right here? 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 I know two things. You know what? I know the third thing. How many ohms must that be? How will I calculate it? What will I type on my calculator? What did you type, Brady? 5 divided by 8? Yes? 0.625? Yeah? Ohms. So these are sort of like brain teasers. You kind of hopscotch your way around, Grace. You keep doing loops. You keep doing other loops. And as soon as you know two things, you can find anything that's missing. In fact, if I wanted to, I could calculate power here, and power here, because it would be, 40 watts, V times I, right? This one's also easy. 35 watts, V times I. 35 times 7. 245? Yeah? Light bulb? Something smaller than a light bulb? PlayStation. Or stereo. 250 watts. That's some kind of bigger electric device, like a stereo, PlayStation, or something like that. So I can even start to tell you what appliances these might be. Is that okay? I think we're going to do one more and we're going to pause. Maybe we'll do more than one more. We'll see. Okay. By the way, you guys are doing great. Trevor, this is Physics 12. Getting the hang of it, though? Trevor, let's go skiing together. It's a nice sunny day, shall we? This way, downhill, 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 downhill. Trevor, my friend, did they tell me how many amps are leaving the battery? No. Oh, wait a minute. How many amps are right there? How many amps are right there? How many amps are right there? I know how many amps are leaving the battery. See, as soon as I know that this question's going to fall apart, Trevor, trust me, it's solvable. Okay? How many amps right here? How many amps at this junction? Still. How many amps went this way? I don't know. Wait a minute. Do I know two things? Then I know three things. How many amps are there? How'd you calculate that? Yeah. Okay. You guys tend to say you're okay with all these equations. This is why I spent so much time practicing the equations. If I've done my job right for most of you, this will be plug and chug. So you said 3? I agree. How many amps were up here coming in? How many amps went this way? What's my next question going to be? How many amps went this way? How many amps right here? How many amps right here? Hey, you know what, Trevor? I know 2 things. I think I know 3 things. What's the voltage there? By the way, remember this is R. Oh yeah, V equals I times R. 20. All right. The last thing we try now is skiing the 2 ski runs. Trev, can you see one of them is going to be this circle here? And the other one is going to be that one there. Okay, let's try the small one first. And the only reason I'm trying the small one first is I know more on this leg than I know on that leg. How high are we starting? 70 volts. Do I know how many volts I lose there? No. How many volts do I lose there? How many volts do I lose here? Did I get to the bottom? Ah. How high did I start? 70. How many did I lose in these 2 grand total? 35. For this, how many must I lose in this one here? 35. Hey, Trevor, knock, knock. Knock, knock. I know 2. That means I know the 3rd one. I got to calculate it, but what's the resistance of this have to be? 7. Oh, nice. You see, these are kind of like little brain teasers. You hopscotch your way. I really view these, Brooke, as physics jigsaw puzzles. I kind of honestly find them kind of addictive. These are sort of like Sudoku puzzles to me. Once I get going on these, it's like, yay! We're not quite done. Trevor, let's ski the outer run. So you ready? How many volts did we start with? How many volts do we lose going down this hill? Everyone goes down this hill. Now we split up. I don't know. How many volts did I lose going through this hill? How high must that hill be then? Let's see. 70. I lose 35. I lose 20. What must that be so that this will also add to 70? Don't think so. Try going 70 minus 35 minus 20. Is it 15? Okay, now I'll show you. Ready for a quicker way? You and I are skiing together, okay? And right here, you and I decide to split up. We're going to shake hands. I'm going to go this way, you're going to go this way, but we're going to meet up. And this may seem obvious, but if you and I meet up, we must meet up at the same height on the mountain. You can't be further down than me. There's no way we can meet up, okay? How high was the hill that you went through? How many volts? I must have lost 15 volts. Otherwise, how could we have shaken hands and met up? We must have gone through the same ski hill height. Otherwise, how could we start at the same height and end at the same height? So if we shake hands and meet up, I'm telling you, this has to be... Knock, knock. I know 2 things. I know 3 things. How many is 7.5 ohms? Is that right? Could you, if I asked, also figure out how many watts each of those is? V times I, 35 times 5, 15 times 3, 15 times 2, 20 times 5. I can tell you how many watts I use in each of those. Is that okay? I fibbed a bit. Let's finish with this one. This one went glitchy on me. I couldn't get it to work. This line here is supposed to be right there. And you know what? I'm going to get really, really, really clever. I'm going to go... No, I don't want to do that, Mr. Dewick. I'm going to go show the ribbon tabs. And I'm going to go color. And I'm going to go like that. Nope, that didn't... Oh, there we go. No, it didn't work, Mr. Dewick. Okay. Can you just imagine this line isn't supposed to be there? I was going to try and color over it with white ink, but for some reason that's not working for me right now. Draw. There it is. Color and thickness. White. Okay. There. No one noticed. Him. Let's go back. Ready, Martin? Let's ski. Downhill. Yes? Downhill, 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 downhill. Yeah? Okay. Did they tell me how many amps are leaving the battery? No. Oh, well, wait a minute. Do I know 2 things? Then I know 3 things. I can figure out how many amps. Folks, how many amps right here? 4, V over R? Yeah. So Martin, did they tell me how many amps are leaving the battery? Technically no, but mathematically they did. How many amps are in this circuit grand total? 4. So whenever they split up and join together, there's going to be 4. That's the current law. Do I know how many amps went this way? Do I know how many amps went this way? No. Okay, then my next strategy, let's go skiing. I'm going to ski this run only because the outside one has all those extra hills and what's going on. So let's go skiing. You ready? How many volts do we start with? What do we lose going through here? Leaving? 32, take away 8, leaving 20. Okay, 24. 24. Let's go this way. I don't know how high that one is, but can I get back to the ground? Can I get back to the bottom? Oh, how many volts must I lose going through that one? How many volts? Sorry? Yes. Nice. Hey. Knock, knock. I know 2. What's the current have to be, folks? How will you calculate it? What will you type on your calculator? 24 divided by 10? 2.4? Yeah? This is where my skier analogy breaks down, because what's 0.4 of a skier? Oh, whatever. Martin, how many amps did you say this hill started out with? Grand total? How many amps went this way? How many amps must have gone this way? Yes. In fact, it's got to be 1.6 amps right there. Yes. And 1.6 amps right there. Right? Oh, look at that top resistor. I know 2 things. What's the resistance of that? V over I, right? 10 divided by 1.6? What is 10 divided by 1.6? Sorry? 6.25? Ohms? Okay. Do I know 2 things here? Let's go skiing. How high did we start out here? What did we lose going through this hill? So, yeah, good. Keep going. I don't know how high this hill is, but what do I lose in this hill? And that gets me to the bottom. How many volts must I lose in that resistor? Isn't this nice? Oh, knock, knock. I know 2 things. I know 4. 14 divided by 1.6. This one is going to work out probably with a repeating decimal. No, maybe not. Sorry? 2.75? 8.75. And resistance is measured in ohms. There it is. We're going to practice this more next class, but I'm going to pause here